cylinder, take a look at the size of this. This proves you're in Switzerland. There are the Alps, okay? And Lake Geneva. And here's CERN. And we've got like basically farmland, the whole area. This is miles across. I think it's almost a 20-mile trip around. At that point is where the particles collide. And of course, based on E equals mc squared, there was a prediction that if everything else we understood about elementary particles was right, there should be an even heavier particle that no one had ever seen, which means bigger M. And Einstein says you can make that if you can put enough E into the picture and convert it. And so this puts in lots of E, and the collision turns it to M, and the Penn detector implied that everything was happening that should happen if the Higgs boson existed. And consequently, they could declare, after observing all of this, that it had worked. And I have this picture here because I really want to get across the fact that A, science works, but B, that the people who do science are at least as excited about it as the people who do anything else. And right now, probably there are idiots in Alabama hanging banners all over the place because their guys won. Well, this is the announcement that the Higgs boson has been verified. These are the 5 guys who, back in the 70s, when their hair was a lot darker than that, predicted that it should exist. I think one of these 2 guys is Peter Higgs himself. Okay, but lurking in the corner, look at this. There's a banner. In fact, it's this banner, and these idiots hung it. That's right, no respect for propriety. Okay, they are Penn grad students who were very much involved with what was happening, and they were really psyched that Penn was part of it. And so they went to this announcement and hung a Penn banner. And these guys are a lot closer to your age than my age. This is part of science, and it's critical to get that sense. I mean, the people doing science here are really, really excited about what they're doing, and they're doing really important work. And that's what goes on at a research institution, and that's one of the reasons it's neat to attend a research institution, because the people who are actually writing the sentences in the book are in the building. And it's also worth taking note, this is work that took 20-some years. I mean, sometimes you don't appreciate the fact that virtually every sentence in your science book is the result of somebody's entire life. It isn't an opinion, it isn't lightly taken, it takes a long, long time to get that information and to get it accepted by the rest of the folks in the scientific community. And it's kind of neat to watch it happen, and you're in a place where it's going on. So that's a kind of a neat opportunity, and you know, if there's anything to the atmosphere of where you do something, this is a good place to learn science. Okay, so let's briefly talk a little bit about science. Okay, is this a scientific statement? Yes. I was off doing research, you know, while I was shopping at the grocery store, and you know, this is a pretty silly thing, right? At least we would think it is, all right? But it turns out that is truly a scientific statement. Because lurking at the heart of a statement, you know, what kind of statements can science deal with? Well, the critical issue is, can we prove that it's right or wrong? That's it. It isn't a right statement or a wrong, it's a provable statement. Now, maybe it's wrong, but that's the point. If it's a statement that we cannot address with verifiable evidence, it isn't science. That's not to say it's not important. There's some awfully important statements in the world that are not readily verifiable. This is, however, this is a good scientific statement because of this. Dun, dun, dun. That's right, it was published October 8, 1996. So we can pretty well verify whether or not this was a correct statement. We can go collect evidence. And of course, you know, as I said to a number of the other groups, it probably did end because, you know, is there anything more heavenly than being at a physics lecture? Right? So you've all died and gone to heaven here, okay? But in fact, we probably noticed no blips on October 15th, 1996. Okay, nothing big changed. And so this was probably an incorrect statement. Okay, however, it is a statement that we could do science with. This, however, is a statement that I wish we could guarantee, but that's not a very scientific statement. Okay, attending Penn physics demonstration shows, okay, what does that mean? We don't have metric units of better. We can't check on your betterness when this is over, okay, and find out how we've done. Okay, we haven't established a point in time when that would be verifiable. And so this is an opinion. This is a statement that, you know, you might hear from an advertiser or a politician or any of those scumbags who make unverifiable statements. Okay, but they're being extremely careful that they don't have to own up to anything in the following months or years. Okay, scientists, on the other hand, do. Okay, and so they take a lot more time. So we're going to talk about light today. And light is of interest for the reason that almost any other physical phenomenon is of interest, and that is it's part of the world around us. Okay? So that's kind of obvious, but it's interesting for another reason, and it may be one of the most important things we can study in science, and that is because along with being a natural phenomenon, it is the natural phenomenon through which we get about 3/4 of our information. So it's also the messenger. It's not just the message. And that means that we need to understand it well. We need to understand what we can count on and what we need to question about the information that comes into us through light. So for instance, we've got a picture there that we can observe, and I can say, well, what do we have there? And we could say that it's a hexagon, but we could also say maybe it's a cube, and you would say, well, what do you mean? And I would say, well, if we shifted it a little, that could certainly be a cube. Okay, now, what's the difference? Well, the difference is that we are predisposed to look for simple patterns. When we portray it this way, the simplest explanation is that it's two-dimensional and it's hexagonal. But if we do it that way, that is a messy two-dimensional picture, but it's a really clean, symmetric three-dimensional picture. And so it's not very hard at all for us to interpret this, and it may not be a cube. It may be some weird link of train stations in some city in Central Asia or somewhere, okay? However, it's very easy for us to say, well, you know, I can remember that better if I think of it as this nice single three-dimensional unit. Okay, so let's take a look at what goes on when we try to see things. Up on the ceiling, I have got a mirror ball. Dun, dun, dun. And we were actually, the superintendent of the building came to me this morning and he said he got a complaint from somebody who tried to use this. We set this thing up last week. Somebody who tried to use this thing one evening last week who said, well, they had a party in DRL and they didn't take down their mirror ball. Okay, and apparently they had no appreciation of the fact that we were doing science. Okay, but you know, they got annoyed that there was this big black disc in the middle of their screen when they projected it. But we have that there for a reason. The light that's being projected onto it, we have spotlights, but what we discovered was that the annoying shadow that we have is produced because the light from the projector that was supposed to hit the screen hits the mirror ball and bounces off, and we get these dots all over the place. And I don't know how well you can see if you're up close. You can actually see the pixels in those things. Notice there's a little grid, and that is the pixels of the projector showing up on that behavior, or you know, from the reflected mirror. All right, but the critical issue is that that mirror ball's doing what every object in the world does. Light is hitting it, and the light is scattering out in 3 dimensions in all directions. So when we say that that mirror ball is there, if I were to say to you, you know, first person to hit that mirror ball with a spitball gets taken out in handcuffs, okay? And you say, wow, that would be so much better than sitting through another hour and a half of physics, okay? I'm gonna try. So what would you do? Well, you would estimate where it was. Now, how do you do that, okay? Well, if you are Mike from Monsters, Inc., you're in trouble, okay? Because Mike has monocular vision, okay? And so Mike is going to look up at this mirror ball, and one of those reflected beams is going to come down to his eye, and he's going to be able to say definitively the mirror ball is somewhere along that line. But he really will have a hard time telling you where, okay? However, most of us, unlike Mike, have two of these, okay? And with two of these, I can get a report from this eye that it's along that line, and 2 or 3 inches over, okay, depending on how strange my face looks, okay? I can look up and get another view, and what I do is I visually converge those lines. And the point where those lines come together is where I locate that object. So we've got a mirror down here, and in this mirror, we see a mostly good-looking crowd of people. Okay, certainly want to include a qualifier there. When we look into that, we realize that Lewis Carroll was right in titling his book Through the Looking Glass. In other words, what we see in there doesn't appear as if it's right on the surface. It appears as if it's on the other side. Okay, so if Mike is checking out his eye, okay, what we see is an object 6 inches away from the mirror here, and then an object on the other side of the mirror. Now, what does that mean? Well, it means that as we view this, let's say that we're just looking at Mike's eye. We have light from his eye coming in and hitting this eye, and then light from his eye is coming in and hitting that eye, and when we track back, those lines do not come together at the mirror. They still haven't converged at the mirror. They're coming together, and we have to imagine that the place they come together is back here where you can't see my hand. And that's working so well that it's believable that he's behind it. It's so believable, in fact, that years ago when I had a parakeet in my first apartment, we had a hallway that went down to the bedroom, and the mirror was over the bureau right across from the doorway. So when you flew down the hallway, if you were a parakeet, you looked there and you said, well, son of a gun, there's another door and another hallway. I'm going to keep flying. And the parakeet would smack into the mirror and knock himself out. And we'd have to move the bureau, pick him up off the floor. He did that a few times. And he did seem to learn something. He learned that every time he went down the hallway, he got smacked in the head. And so he wouldn't go down the hallway with us. Like, he would sit on my shoulder, and I could make believe I was a pirate and the whole deal. But if I walked down the hallway, he would fly back to his cage. Because he knew that, I was going to walk into the wall and smack both of our heads. Okay? So it's convincing. Now, of course, we grow up and we learn about mirrors, and we learn that you can see little irregularities and that works. But nonetheless, the appearance is something worth noting. It's worth noting because if we don't know the rules, it seems like we can break the rules. So this mirror is this high for a reason. And that is because if it were any higher, I'd be really uncomfortable doing this demonstration. Okay? But in this case, now you can't see my left leg, except everything looks just fine. Okay? And it looks just fine because if we can sneak in a word from that bogus science biology, I have bilateral symmetry. Okay? And that means that if you draw a line right down the middle of me, most of my body parts match on either side of the line. And so my left leg is very similar to my right leg. And so a reflection of my right leg looks like my left leg. And if the mirror lines up with my axis of symmetry, this all looks like it takes place. So given this arrangement, it looks as if you're looking at a whole person here. Newton's third law says I can't lift myself off the ground. And it says that because if I lift something up, I do that by pressing down on the floor, right? And of course, there was always that metaphor of picking yourself up by your bootstraps. And so, you know, if you could do that, right, somehow you could pull up and not have that reverse force, that opposite force. So with this, we could actually take a picture of violating a law of physics. And we need to know that. We need to know that there are going to be visual alterations that appear to break the rules. We need to know that it doesn't have to be a UFO. It could be refractions in, you know, moist air. It could be mirages. It could be anything. It could be reflections in a plane mirror. But nonetheless, and I've practiced this really hard. It was easier when I was young. As I get old, it's even harder to pull myself up by my bootstraps. Okay, but we should still be able to do this. It's tough. Okay, let's see. You got that picture? Okay, is it working? Well, it's working so well that I can just kind of stay here. And of course, I could use this to get rich and famous, right? I could have hang time that beat Michael Jordan. Okay, I could maybe fly. Okay. And in every instance now, because we've got this symmetry, we can create an image that would fool us, okay? So this is one of the reasons that we really need to know the rules. We need to know when we can believe what we see and when we need to be skeptical of what we see. The image that we see in this mirror is called a virtual image. Physicists had that word long before, you know, video game guys did, okay? But it's got the same meaning. It means that we have simulated a reality. We don't really have it happening. The virtual image is the appearance of an origin of light in a location where no light ever really got, okay? We've got that light scattering in such a way that it appears to, you know, there appears to have been an object that caused it, but it's not really there. We have a second case. I don't know if you've been paying close attention to this. This is a curved mirror, okay? And the curved mirror obviously acts a little bit different than the flat mirror. And what we have managed to do, I realized that in order to see the effect, you need to be standing right about here. And so to do that, we've placed a camera. Because I can't get everybody's eye up here at the same time. We'd like you to be somewhere in that zone. But if you're in that zone, that's the view you get. And if you're wondering, okay, that really is a real-time view, okay? So that's happening right now. But if you look on the screen, there's 2 light bulbs. But if you look in the case, we're missing a bulb, okay? Now, that's so real, in fact, that if I move around a little, the bulb stays right there in the socket. Okay, I mean, that's a pretty convincing deal. Now, what's going on? Because this mirror is curved, instead of that light appearing to come back in straight lines, it comes in here, converges up to this location. Now, what light? Well, the view that the camera has of this light is the light from the front of the bulb. The light from the back of the bulb normally would just disappear out the door. But we have gathered it, reassembled it, and it's right there. If there's any question about that, when I block the back of the bulb, you can see my hand comes in and blocks the top bulb. Okay? And so we end up by taking what you would have seen at the back of the bulb, collecting it, and having a class reunion of light waves right here. But they come together and then begin to scatter, okay? And if we take our eyeballs here, remember, how do we see this light? We see the light by noticing the light rays coming from one location. Well, the light rays up here are doing the same thing. Our eye is seeing them, or the camera is seeing them, and coming together and saying, right there is where they were. There is a wonderful applet available. It's called the thin lens demonstration, and Fu Kun Huang wrote it in 1996. His website is no longer supported, but this is good enough that a number of universities are supporting it. If you Google thin lens applet, you will get, this one I think we're getting from what, Hawaii, I guess? I don't know. There's a couple of universities. It's a local company. But we've got these diagrams here. This is a curved mirror. Notice I can choose mirror or lens. This is the focal point. Here we've got the object. Now our object is down there, right? And I can do that. So there's the object. And notice if the object is here, the image shows up on the top. Okay? Now what's happening? There are an infinite number of light rays leaving the tip of this object. We know what 3 of them are going to do. So we can draw a ray diagram. We know the light ray parallel to the axis of the mirror bounces off through the focal point. That's the red line. The line through the focal point bounces off parallel to the axis. And the line that hits dead center in the mirror bounces off symmetrically. And they reconverge there. Now, that's the drawing you see in your book. I looked at that drawing all the time I was in high school. I got through most of college. You know, they're pretty pictures. They didn't mean anything to me. Let's turn this around, however, so that I can access the thing on the bottom. And let's grab our eyeballs. The thing that's missing from this picture is that these light rays come down. They don't stop there. They keep going. The observer is down here. We've got an eye looking at this light ray. We've got an eye looking at that light ray. They're saying, you know what, those 2 rays seem like they came from that one place. I think that there's a light bulb there. If we get the observer in the picture, we understand what the ray diagram is telling us. These are really, this is a neat thing, because once you understand that, you can play around with it. So let's take our light bulb and put it right here, and look what happens. If we are 2 focal lengths away from the mirror, the image is exactly the same size as the object and in exactly the same place as the object. And that's what we've done in this case. Here is the object, and if I remove the object, okay, I remove both of these guys. If I put him in here, the pattern is so symmetric, I get the object down there. Of course, I'm at the edge of the mirror, where just like the Hubble telescope, we screwed up the geometry of the mirror and we have, you know, a distorted image. Okay? We haven't corrected it with any optics, but needless to say, you can see that the effect is the same from both places. Okay, and here we get a really good one. So this is the way that we explain that. I would certainly commend this to your attention. The other thing that's really neat is that I can switch to a lens. The lens has the same focal length, and I can suddenly see that I get to use the same equations for both objects. All the geometry is the same. It's just that in the case of a lens, the light passes through and changes direction on the other side. So lens systems bend the light, mirror systems bounce the light. The bending is refraction. We're going to talk about that more with a couple of further demonstrations. Once again, this is fully animated, and you can say, well, what happens if I get far away? What happens if I get close? And wow, if I get close, look at that. I get this. What does that mean? Well, it means if the eyeballs are over here looking at the light doesn't come together in front of the lens. It comes together behind the lens, and the object looks bigger. In fact, it's bigger and right side up, and it acts like a magnifying glass. And so now my incredibly small nose finally looks like it's the right size. Huh? Okay. So if I'm up close, I get to have a magnifying glass. If I'm really far away, it inverts and I get a real image. Okay, let's see if that description really passes muster. So we'll take this thing, we'll pull the bulb out of the picture, and in fact, and this is a really neat, this used to be an expensive thing that only I could do here at Penn, but laser levels now, we got these at Harbor Freight. We waited for a sale, they were $4 a piece. Okay, so I could do this really cheap. And so I've got 5 light beams, and you know, I can squirm them around and get them just about right. And we can run these 5 light beams in here and have them run into the mirror. Okay. I can adjust this a little bit. Okay. Now you can actually trace this around with a piece of paper. Okay. So here's the original light, and if you notice, it's on the paper and it's pretty parallel. But now I come over here, and here's the light coming off of the mirror, and it comes together, comes, boom, there's the focal point. And where is the focal point? Exactly halfway out to where the bulbs were, and then it spreads. And if I move this like really fast, you can maybe visualize it, but boy, that's so much more work than a smoke machine. So let's see what the smoke machine shows us. Okay, so look at this. I'm breathing this crap just to do physics. So I don't know how well you can see. The light beams are coming together right here. Here they are coming in. Here they are going out. This is absolute gangbusters if you're looking along the line of the light, but I think we've probably got it dark enough that you can see some of that convergence. And the critical issue is, and why is this of merit? Because you need to know that the mathematical model you're putting on a piece of paper actually represents a behavior. Okay? It is something that portrays the event you're trying to explain. And so once we've seen this diagram, we can go back to the thin lens applet and actually produce results that we know are not some fantasy, that they really are the event that takes place. How about a lens? Well, if we take a lens of the right size and put it in here, okay, and get these guys to go through it. Okay, let me get this out of your way so you can watch things happen. Okay, so here are the laser beams on the wall having passed through the lens. And of course it might be easy to say, well, they just passed through. But once again, let's track them. And so if we take a piece of paper here, all right, we find, there's the focal point right there. And now things cross over and run into the wall. And the interesting point is, if I come in and block the top guy, it's the bottom one that gets messed up. If I block the bottom guy, the top guy disappears. And all of that is because this whole thing is crossing over right there. And once again, with a little smoke, we can see how well our ray diagram represents the behavior that we're talking about. Okay, and this is, you know, pretty neat. How are we seeing that? Okay, from over here, you guys are getting a half decent look there. Okay. So that's looking pretty good. Okay, we can bring lights up. I'm sure this is good for you. Can't imagine that this is anything but wonderful. Okay. this thing out here. Yeah, we're gonna pull this all out. I think this is
or if you download the QuickTime Pro, which costs a little bit. It's not bad. You can just say like start and clip them out.
Maybe I should cut it. Maybe I should cut it.
Ah, sure.
Because there's